All right, y'all go ahead and do the factoring and the math knowledge question for today. Pause the video, and then once everyone is finished, you can unpause the video, and I'll go over the correct answers. So for this one, you're going to have to do remove, replace, reduce. So we're going to have, instead of a 30, 210. So you want to replace your 7 that you removed. And the numbers that you're going to use are positive 35 and positive 6. 7 and 35 both divide by 7. So you have x squared plus 5. And then the second factor won't reduce. So this would be your answer. For the math knowledge question, we are looking at the equation of a circle with the center of 4, -2 and a radius of 3. Well, our formula is x minus h squared plus y minus k squared equals r squared. Our radius is 3, so that means that it should equal 9. So we're going to go ahead and eliminate a and b. This is my h value, and this is my k, so I should have x minus 4. And the only one that does that is e, and then it's going to be y plus 2. So that's your equation there. So we're looking at lesson 85 today. The mean value theorem, and then the application of the mean value theorem. I'm frequently going to abbreviate the mean value theorem as just MVT instead of writing it out. So hopefully you'll understand the mean value theorem and how to apply it after this lesson. So the maximum minimum value existence theorem. This is a theorem that we have discussed a little bit. We haven't proved it, but we have discussed it just a little bit this year. If you have a continuous function f on the closed interval from a to b, f obtains a max value m and a min value little m on your interval. So if you have a continuous function on that interval, you are going to have some max value and some min value. So that's the maximum minimum value existence theorem. But you have to have a continuous function in order for it to work. The intermediate value theorem is another theorem that we have discussed. We haven't proven it this year, but we have discussed it. If f is continuous on the closed interval from a to b, and n is a number in between f of a and f of b, then there is at least one number c that is in between a and b, for which f of c equals n. So I'm going to draw a picture for this one quickly. We have a, and we have b, and we've got our function. So this point is f of a, and this point is f of b. And n is somewhere here. That means that there is a c value right here that will produce that n value. And so if we move n further down, if that is our n, then the c value would be here now. Or if you put your n here, then your c value would be here. It's just saying that if you have a continuous function and n is in between f of a and f of b, then you have a c that is in between f of a. That is in between a and b. Okay? So now looking at the mean value theorem. If your function f is continuous on your closed interval from a to b, and if it is differentiable on the open interval from a to b, then there exists at least one number c in your interval such that the derivative at c equals f of b minus f of a over b minus a. These are your x values. These are your y values. y2 minus y1 over x2 minus x1. That's just your slope, which is what your derivative is. And it's just saying if you have a continuous function and it is differentiable, then there is some number c that actually equals what the slope from a to b is. So if I have a function here, and I'm going to look at this point to this point, and you connect it. At some point here, the slope of your graph is actually going to be the same as the slope of the line that I drew in. And it exists at c. It doesn't tell you how to find c, it just tells you that it does exist. So that is the mean value theorem, MVT. Not MVP, MVT. All right, so let's look at the first example. We want to demonstrate an understanding of the mean value theorem by applying it to the function f of x equals x squared minus 2x minus 8 on the interval from -2 to 1. So we are going to first figure out what f of -2 is and f of 1. F of -2, if you plug in -2, equals 0. And then f of 1 equals -9. And so now we're going to use the mean value theorem. And I'm going to write it out for you. Our b value is the 1. So what is f of 1 minus f of -2? And then we have 1 minus -2. I'm going to come up here. Your f of 1 is -9. Your f of -2 is 0. And then we have 1 plus 2. So I have -9 over 3, which is -3. So our derivative at c is -3. So what the mean value theorem guarantees, for some number c in between -2 and 1, the derivative, or the slope of the graph, equals -3. But it does not tell us where that actually happens. So it tells us that it is going to equal -3, but we don't know what the c is. So that's as far as you can go. You can't actually figure out what the c is. It just tells you that it exists, and when you plug it into the derivative, you're going to get a -3. So let's look at the next example. The value of the function f of x equals 1 over x squared minus 1 equals 0 at x equals -1 and x equals 1. And the line connecting the points is horizontal, so the slope of this line is 0. Determine whether the MVT can be applied to prove the existence of a point between the x values of -1 and 1 for which the slope of the tangent to the graph of the function equals 0. So, to use the mean value theorem, we first have to have a continuous function. Well, if we graph 1 over x squared minus 1, 1 over x squared looks like this. The volcanoes at the y-axis. And then if it's -1, it got shifted down by 1. So is that a continuous function? No, because at 0, it does not exist. It's not defined. So determine whether the mean value theorem can be applied. Can it be applied? No, because it is not a continuous function. So that's all you would do. It's not a continuous function, so it can't be applied. Looking at the next one. Demonstrate an understanding of the mean value theorem by applying it to this function on the interval -8 to 27. So we start by looking at the graph of it. X to the 2/3 looks something like that. It is a continuous function. However, if you try to take the derivative of it, you will not be able to take the derivative here. And the way you can confirm that is by actually taking the derivative. And if you rewrite it, you have 2 over 3 and the cube root of x. This does not work when x equals 0. It's not, it does not exist. And you can't take the derivative of this at 0. It's not differentiable at a sharp point. So can we use the mean value theorem? No, because this function is not differentiable. So demonstrate an understanding by applying it to this one. You say it can't be applied because it is not a differentiable function. So it cannot be used. You could find a c and it shows you in the book, but it's actually outside of the interval that they give you. But you can't actually use the mean value theorem because this one is not differentiable. Even though it's continuous, it's not differentiable. Looking at this next example, we have the function absolute value of x minus 1. Does the mean value theorem imply that f prime of c equals 0 for some number c between -1 and 1? Well, we need to check two things. Is this a continuous function? Well, an absolute value minus 1, it's a v shifted down 1, so this is -1. That is a continuous function. Is it differentiable? No, because we have a sharp point here. Remember, the left hand and the right hand limits are not going to be equal. This one is going to be a -1, and this limit is going to be a +1. Those don't match up. So the mean value theorem cannot be applied here. I know you feel like half of the question, or it was really 3 out of the 4, we could not even apply it. Sometimes that happens. We can't actually apply the mean value theorem here. So it does not imply that that is true. Okay, so now let's look at application. We have a theorem. If the derivative of a function equals 0 for all real values of x, then the function is a constant function. Another way to write it, it's more formal. If your derivative at c equals 0, then there is f of x equals c on the interval for some constant c. Okay? And then looking at another theorem, if we have two functions, f and g, that have the same derivative for every real value of x in the interval, then they just differ by a constant. So if the derivatives are the same on some interval, then if you subtract them, you're going to get the constant. And so that would be like if I have two parabolas, this one here, and then this one here. They are the exact same, except for this one is shifted up by 2. So if I took my f function and my g function and I subtracted them, I'm just going to get a difference of 2 for my c, because that's all that they differ by. So that's what it was saying. Now looking at Rolle's theorem. If you have a continuous function on a to b, and if f of a equals f of b equals 0, and if it is differentiable, then there exists some number between a and b such that the derivative equals 0. So it says you have to have a continuous function and it's differentiable, and at your endpoints, your function has to equal 0. Then some number c exists between a and b such that the derivative at that c equals 0. Okay, so it'll ask you to actually use that on your homework. Let's go to your homework really quickly. On number, we'll look at number 9. It says, let the function be x squared minus 4x plus 3 on the interval from 1 to 3, and you want to confirm Rolle's theorem by finding c such that the derivative equals 0. And so you use you would use Rolle's theorem by taking the derivative of your function and that would be your derivative, and it says that at some number that equals 0, and the number is c. We don't know what it is, but at some number it equals 0, and so your c value is 2. And so it says some number exists between a and b such that the derivative equals 0, and so your c value is 2 there. So that's basically what you do with Rolle's theorem. They don't have an example in the book, but that's one from your homework for tonight. So let's look at an application of the mean value theorem. The speed limit on a highway is 65 miles per hour. At 6 p.m., a police officer sees a truck go by at 60 miles per hour. That officer radios another police officer 70 miles down the road who sees the same truck go by an hour later at 7 p.m., traveling again 60 miles per hour. Find the average speed of the truck between 6 and 7 p.m. Well, your average speed is just your rate, which is the total distance you traveled over the time. Well, how far did he go? 70 miles, and it took him an hour. So his average speed was 70 miles per hour. The truck driver is ticketed for speeding, but he argues that he was never clocked over 60 miles per hour, which is a true statement. The truck driver is convicted by a judge who points out that he must have been traveling 70 miles per hour at least once. Is the judge correct? Well, yes, the judge is correct, because there is no way for him to have gone 70 miles down the highway within 1 hour unless he had to have been going at least 70 miles per hour at some point. So if the driver did not exceed 65 miles per hour for an hour, he would not have been able to travel more than 65 miles in that hour. So that means that the driver had to have been speeding. By the mean value theorem, the driver's speed reached 70 miles per hour at least once between the time 6 p.m. and 7 p.m. Now, is that likely to ever happen in real life? Probably not. But that's what the book says is an application for the mean value theorem. So hopefully that kind of makes a little bit of sense there. On your homework, you don't have any to omit, so make sure that you do that tonight. And then we'll go over any questions you have tomorrow.